This is now part 2.3 of the lecture where we're discussing about finite hypothesis sets. Now here we are actually concerned about inconsistent case. Now what does inconsistent mean? Well, we saw in the consistent case that the algorithm was able to return a hypothesis which had zero error on the test sample, right? Inconsistent means that the algorithm returns an hypothesis which does not have zero error. Basically, no such hypothesis exists which is right on all samples. And if you think about it, that's how things are in practice. You cannot actually get zero training error, right? Training error. We have something which is inconsistent on all the training samples at least. So what do we do in this case? So no H is a consistent hypothesis. The typical case in practice, difficult problems and they have complex concept classes. But inconsistent hypotheses with a small number of errors on the training set can still be useful. So we need a more powerful tool, which is the Hufting's inequality. And we learned about the Hufting's inequality. What the Hufting's inequality is a probability bound which bounds the real risk of an hypothesis away from its empirical risk, basically. Basically, it says how much it deviates. So if you look at these two statements, the probability that the real risk is epsilon higher than the empirical risk is less than some exponential. Similarly, probability that the real risk is epsilon lower than the empirical risk is another exponential, same exponential. So this is, we can combine these two by the union bound whatever, and say that the empirical risk deviates from the real risk by epsilon in either direction can only be less than, well, add these two, so twice of epsilon, some exponential. And this Hufting's inequality you have to look up or look in the other video. What are the conditions on the random variable, what other things you need to impose, etc. But this is the inequality that we are working with. And now you can see it's pretty easy. Now if we had the empirical error, then we can comment on the real risk based on the Hufting's inequality. But how do we do that? So the first question is, how do we apply it to the learning algorithm? Can we apply that bound to the hypothesis H sub S returned by our learning algorithm when training on sample S? No, because H sub S is not a fixed hypothesis. It depends on the training sample. If you change S to some other, even if you train one training sample, your hypothesis can be completely different and therefore its bounds could be completely different. So now if you note, like if you look at this, the expected value of the empirical risk on this particular set is not a simple quantity because it also depends on the sample S. So we need a bound which holds uniformly over the entire hypothesis class, like capital H, a uniform convergence bound, it's called. And this is easy in this case because we have a finite H. Like the finite, there is an innumerable number of hypotheses. It's a finite number. What we will do is look at the probability that the maximum, like the worst possible, if I pick the worst hypothesis, it deviates from its empirical risk by greater than epsilon for a given sample. For a given sample of all the hypotheses, the one which has the highest deviation of its real and empirical is the one we are concerned about. And what we will see is that if the probability that the worst is greater than epsilon, if we can bound this, then what we can say is that if you are able to bound this, that the worst possible hypothesis has this greater than epsilon, and if we can bound that probability by some number, the probability that the worst hypothesis will have some number less than epsilon is greater than 1 minus delta, right? Again, you're going the same routes which we have seen so far. If we can bound that the worst possible is greater than epsilon, and if we look at the reverse of that event, that is the worst possible hypothesis is less than epsilon, that means whatever hypothesis our algorithm has returned will definitely be less than epsilon because the worst is also less than epsilon. So let's try to bound this probability that the max of this number is greater than epsilon. We can do this by saying that probability of the first is greater than epsilon, or the second is greater than epsilon, or the third one is greater than epsilon, or blah 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 up to the total number of H. and then use a union bound on this inequality, which is an overkill, but we do it. And for all h, no matter what sample you give, the probability that its risk deviates from its empirical risk by more than epsilon for every h. And now we know this quantity from the Hofding's inequality. It is some exponential in minus 2m epsilon square and 2 times the number of total hypotheses that we have. So from this, what we have here is the probability that the max is greater than epsilon. So the probability that the max is less than epsilon, probability that the max of this is less than epsilon is greater than 1 minus this number. Now the probability that the max is less than epsilon, that event happening that the max is less than epsilon means whatever hypothesis I have returned is also less than epsilon. So whatever hypothesis my function will return, no matter what the sample is, will have something less than epsilon with probability 1 minus delta. And this number is delta basically. I set this number to delta, I solve for epsilon, and what I get is that the risk is less than empirical risk plus some square root log 2 delta by 2m. How does this happen? Let's see. If I make this equal to delta, I take the 2 below, so it becomes delta over 2. I take the h below, so it becomes delta over 2h, and because of the exponential it becomes 2h over delta. So 2h over delta, and take the log of it. So it's log 2 over delta plus log of h, and which is what we see in the numerator. And now that we have to divide by 2m from the right hand side, it becomes this, and then because of its epsilon square we have to take a square root. So this is equal to, if I set this as delta, this is what epsilon is. Essentially just, write it in your, pause the video and write it and you'll figure it out, it's fine. So thus for a finite hypothesis set with high probability, what we see is, because delta is a small number, we always give this high probability bounds. With high probability, what we see is that the risk is less than the empirical risk plus some small number, which goes by 1 over square root of m. So error bound is 1 over square root of m, which we say is quadratically worse. So the log can be interpreted as the number of bits, again, whatever. So now as you can see what the Occam's razor principle is, that plurality should not be posited without necessity. We will Occam's razor principle will come back again. So what this means is that we'll talk about Occam's razor principle in the next video when we talk about infinite hypothesis set. I think that is a better way to talk about Occam's principle. But Occam's razor principle says that you can keep increasing the number of hypotheses that you have, like start throwing more and more things to it, but that can make things worse essentially, because as you throw more and more complex or whatever functions into this, you're increasing the number of hypotheses and the log term is increasing. So the risk bounds that you can confidently give become more and more looser, so to speak. So the best thing to do for you should be try to minimize the number of keep the hypothesis set as simple as you can, which is what it means. Plurality should not be posited without necessity. Keep it simple without, if it's unnecessary, keep it simple. So or it can be rephrased as the simplest explanation is best, whatever. So invoked in a variety of context, example, syntax, Kolmogorov complexity. And here to minimize the true error, choose the most parsimonious explanation, which is the smallest h, basically. That's what we said. And it's not about minimizing true error, it's about minimizing the true error with respect to the empirical error. So it is entirely possible that if you choose a small h, your empirical error is high. Basically, you just take a function which always outputs a constant. Your empirical error is going to be high. So what you really need to do is find a trade-off, that you can start making h more and more complex. That decreases the empirical error, but that also increases your confidence. Like you increase this quantity basically. That with high probability, how much you can say that the risk is away from the empirical risk. Because if you start increasing h, this number becomes higher and higher. We will see later applications. This is what later applications. So lecture summary of these 3 parts. It is pack learnable. Any complex, concept class is pack learnable. If for the algorithm, for all concept classes, what we have is, if I give you a polynomial number of samples in 1 over epsilon and 1 over delta, the algorithm returns an hypothesis which has low error with high probability. So probably approximately correct. Learning bound for finite hypotheses is just straight up by the union bound and what inequality. How, let's try to come up with this algorithm now. We use the union bound on the fact that some subset of the hypothesis set will be consistent while having a high risk. We made that small subset H sub E, which has a high risk but gives a low error. And how is that possible? That is only possible if it makes no error on m points, which goes 1 over epsilon to the m. So we can prove this again if we want to, if we can write it and prove it again. Learning bound finite hypothesis inconsistent case, this we proved with using Hoeffding's inequality. And the only reason this square root term comes in, because in Hoeffding's inequality we have the epsilon exponential square, exponential minus m square, exponential of epsilon square, right? Whereas in the finite hypothesis case, if you remember, when we write 1 minus epsilon to the m, we approximate it as e to the minus x. So where the Hoeffding's inequality gives us epsilon square, this proof gave us just epsilon, e to the minus epsilon, e to the minus m epsilon, whereas Hoeffding's inequality gave us e to the minus epsilon minus m epsilon square. So this is something that is, that happens because now we are in the realm of probability bounds where things are inconsistent or whatever. So we lost that bit of performance basically. So now the question will be how to deal with infinite hypothesis set, which is the more interesting aspect of it, because you don't really have finite hypothesis sets in reality. You always deal with infinite classes, like infinite neural network with real valued weights, right? So it's infinite basically. So that is what we will talk about in lecture 3, which is going to be a really, really interesting one.